Hi, my name is Pablo Galindo.
And my name is Łukasz Langa.
And this is the core.py podcast, an established podcast when we discuss internals of CPYTHON and our adventures in making a new version of your favorite programming language.
All right, let's start with the most important thing, which is sports news. Karl Mayer's hockey team, the Bellingham High Sticks, won the second preseason game 6-0. 6-0?
Nice.
Yeah,
nice.
Karl actually scored one of those. Unfortunately, in their opening game of the season, they lost 6-3. The silver lining here is that the 3 goals were scored by Karl. So hat trick. So go High Sticks.
Go High Sticks, yeah. Even if they lose 6-3, but well done, Carl.
Well, hopefully they're going to get better, with just one guy actually scoring so many points. The
MVP.
All they need is somebody else to step up, and they should be fine. They will be fine. They will be fine.
Is hockey one of these sports when being super tall gives you an unfair advantage like basketball?
Oh, I don't actually know. All I know is that the league that Karl is in is way different from NHL. So definitely you don't break noses and bones. It's less of a contact sport than what I thought it would be when I saw them live.
Okay. So it's like hockey for kids. Whoa, so it's fire.
It's hockey for elegant people, I guess.
Oh, I see. You know what would be a good name for elegant people?
Yeah, what?
Justin. Our good friend Justin.
Yes, we have a friend who we are gonna call Justin today.
For now, yes, Justin.
Yes.
Yeah,
as we promised.
We'll talk about Justin later in the podcast, dear listeners. But today is a good time for talking about memory management. And why is this? Why we are starting with memory management, Łukasz, even if the poll that we made on Twitter really pointed to garbage collection. So we are literally ignoring the most voted result in the poll. Isn't this anti-democracy?
Oh, I don't even want to go there. I spend too much time looking at US politics now and so on. I don't want to talk about democracy. All I know is that if you want to talk about garbage collection, you actually should mention reference counting first. But if you want to talk about reference counting, you should actually start with how do we even allocate any memory?
Right.
So this is what we're going to talk about today.
Yeah. To talk about memory allocators from the ground up, first you need to create the universe. But we are not going. This is a different podcast.
Yeah. So first you need to create the kernel, but to create the kernel you have to have a CPU to run the kernel on and so on. Yes, you could go all the way down.
Okay. So gross oversimplifications here, but let's talk. So Łukasz, tell us what are these memory allocator things? Why I cannot just is for wait mysterious no this one no sorry I'm being a bit of the shape. I need to control my buttons. So is this one? Łukasz, surprise question. Is malloc a system call?
No.
It's not. Very good.
It's
very
not.
Good. Yeah, nice. We are starting this season very good, not like the High Sticks. Whoa. Okay, so if it's not a system call, then who does the mallocing? Who mallocs the malloc?
Who mallocs the malloc? Well, if you write C correctly.
Impossible. That's a legend. Nobody writes C correctly.
If you write C correctly, then you don't even call malloc. C is a fantastic language that has automatic memory management. Don't you know this? It's famously known for the fact that if you are using C in embedded environments, which I did for a while, writing firmwares for music instruments, electronic music instruments.
Right.
So the trick there is that all memory that you allocate automatically, statically.
Yeah, exactly. It's give me a...
The compiler does it for you.
Give me a big chunk of memory and don't do anything else with that.
Yes.
I will do it myself.
Exactly. So in the C file or in the header file, you just say I need memory for this structure. I need memory for this many copies of this particular data type and so on and so on. And you get that. And it's amazing because it's automatic.
Right.
But obviously, this is not going to work for a lot of regular software. So you have another type of automatic memory management in C, which is the stack allocation, right? Every time you create a variable in a function, what is actually happening is there has to be a space in memory for this. And is created there for you in the stack frame. And when you are calling the function, that memory is waiting for you. And when you are leaving the function, when the function execution is over, that memory is reclaimed. So you don't have to actually do anything there. This is automatically fine for you. Obviously, you can do evil things with that if you try to reference that memory that is stack allocated outside and so on. Like there's plenty of wrong ways to use this.
Evil.
But if you use it correctly, it's automatic.
Right.
But obviously, because of what I already mentioned, like sometimes sort of the life cycle of what you want is not the same as a function call, well, then we need to actually go and call calloc or malloc if you don't care about the memory being zeroed, and so on and so on. So those things actually use up some system calls, mmap and brk.
It's break.
Yes.
Do you know the difference between mmap and brk?
I fuzzily sort of know, like, okay, like mmap, essentially you are using the sort of anonymous heap allocation.
Yes.
Yeah.
It's technically pedantic Pablo. Pedantic
Yeah, let's
Pablo.
go, Pablo.
Yes. So there is okay. So Linux has this concept of the heap, right? And the heap is not what you think is the heap, because like when people say, "Oh, I allocated this memory on the heap," well, probably it's a lie. Like you didn't actually allocate it on the heap. You allocated into, as Łukasz mentioned, an anonymous memory region. That is what happens when you call memmap. So memmap with a bunch of flags, because it takes a huge amount of flags, and you can do a bunch of funky shit like memory map and file, which is like a abstraction, blah blah blah. But like you can say, just give me this many bytes, these many pages of memory, and it will just give you like, here it is in some random place, right, on the memory address. But then it has this concept called the heap, and the heap, it will appear if you are in Linux and then you cat /proc your PID and then maps. It will list all the memory maps of your process, and one of them will be called the heap, and it appears in brackets because like reasons. And the heap is like it's almost like a stack. It's like a linear thing that you can manually grow. So that's what happens when you call brk. So brk basically says grow the heap to this pointer, and sbrk, which is the other one, because brk is kind of annoying because you need the previous pointer. So sbrk says grow the heap by these many bytes. So it says grow the heap, but it grows linearly. So it just moves the pointer a bit forward, and then you call it again, it moves it a bit forward, and you can reduce it with a negative number. So you call sbrk -10, it reduces back. But you can see the fucking problem with this thing, which is like if you have like a memory for an object and then you grow the heap a lot, and then you want to go back, well, you cannot, because you have memory for the object in the middle. So you need to wait until all the posterior objects has been deleted, which is like it's like a second stack, if it makes sense. Like, it's not like memmap, which is like, oh, I just finished with my memory that you gave me with memmap, so I can just free the entire thing, because like, that's the whole world. Here, the heap is like you grows outwards, and then it grows downwards. And
so now I have my own question to you then. So if break and sbreak are so bad, then why not use mmap for everything?
Oh, well, there is many reasons. One of them is that break and sbrk are faster. So that's one of the things, and that is the main thing. And the other thing is that sometimes like managing those is much easier, so you don't need to do less bookkeeping. And what malloc does, at least the glibc malloc, is that it handles both. If I recall correctly, the malloc from Muscle, it doesn't use brk at all. It just uses memmap, just because it's like...
Yeah, that has one consequence, right? What's the unit of memory that you can allocate with mmap?
A system page.
Yeah, an entire page, which is huge.
4K.
Or larger, depending on how you configured your kernel when you compiled it.
Exactly, yes. Like memmap needs to be multiple of pages.
Yeah,
brk needs to be bytes. So yeah, that's the real heap, not like what people call the heap, which is this nebulous concept. Yes.
Right. So obviously nobody actually wants to use mmap and brk directly because they're kind of annoying to use. So this is why we have, high-level memory allocators. And this allows you to actually have something that has algorithms that deal better with memory budgeting if your memory is constrained by size.
Right.
It can help with memory fragmentation. So situations like, in theory, we have so much free memory, but in practice, it is just so badly managed that we cannot allocate a large chunk anymore. You can have stuff like debugging helpers where if you are in some magical mode, this allocator will help you identify problems with your code, and so on and so on. Like some are faster than others, and that really depends on how you're going to use it, which is why we have quite a few of them, right? There's a regular malloc, there's malloc, there's this other that Google uses, tmalloc.
TCmalloc.
Yeah, tcmalloc.
Yeah, that is
and so on and so on.
like thread. Like the malloc is particularly bad at multi-threading. Like because it has a gigantic lock. So tcmalloc is a bit more like thread friendly. So it performs better if multiple threads call malloc at the same time.
Right, and it's amazing that there's so many things that have their own malloc. So Python does too.
Yeah, we do as well. Pymalloc. We like to put py in front of everything.
Right, so pymalloc, is that something that uses mmap and brk directly, or
It uses
like, what are we
everything.
actually
It
calling?
uses everything. It uses all the things. It uses well, it doesn't use brk, but it uses memmap.
Exactly. Oh, better yet, like if you actually want to allocate more than 512 bytes, you're going to use the system allocator. Like the pymalloc is going to be like, no, I'm dealing with smaller change.
Right.
Like this large allocations, let's just use the system allocator. So for those smaller requests, the pymalloc allocator will allocate a larger chunk in memory actually, and then just subdivide this in some magical way. So let's talk about like what the sort of allocation domains are there in pymalloc now.
Right. So this magic number, these 512 bytes, is basically a number that appear from nowhere. It's a good number, and like the idea is that because we are going to restrict ourselves with like a very specific situation. In this particular is allocating Python objects. Like what are the characteristics of Python objects, Łukasz?
Well, okay, there's essentially two. That most objects are small and most objects are short-lived.
Exactly.
So they're just gonna be like, created and destroyed very quickly.
So that's the reason we want a second malloc, not really because we want to participate in the contest of. We also have an allocator, like, but mom, we like we have an allocator at home, the allocator at home. So it's because like we know better than malloc, because malloc is a general purpose allocator, but this is a specific allocator. So it works better if we know exactly what the hell are you going to do with your memory, because then we can do a bunch of smarter things. So pymalloc, when you call it, you need to basically use what is called a domain. You need to tell pymalloc what the hell are you going to use your memory for, and there is 3 domains and a small twist. So the normal domain is called raw domain. So this is just some it's just memory for some general purpose stuff. Like for instance, buffers. Like if you need just scratch buffer to put a bunch of things, or you want to put a bunch of bytes there that really are not going to be in any object at the end. Like that's the raw domain. Like it's just very general, no optimizations. Then there is the memory domain, and this is very specific for Python buffers. So it's like buffers that are going to be part of memory, like Python objects. For instance, one good example is that lists. So list objects, like they have an internal buffer when they put the actual elements, and this buffer needs to grow when you keep appending objects. So that's a good example of the memory domain. And then finally, we have the object domain when you put the actual object. So for instance, in the case of the list object, we will use the object domain for the object that represents the list. But then we will use the memory domain for the actual buffer that contains the pointers, because that is not a Python object, it's just a buffer.
Right. So PyObject, which PyList is going to be one, like PyObject is very small, right? Because it's just essentially our metadata.
Right.
And the actual data lives somewhere else.
Exactly. So these allow us to use different algorithms and things like that. And that looks fantastic and sounds really smart. But and I thought when I discovered this, it's like, okay, this is kind of like cool, right? Because the object allocator can do like a bunch of different optimization, knowing that these wrappers are going to be very small, and then the memory. But then it's like, so what kind of optimizations we do in memory that we do in raw? Because raw is like, I don't know what the hell is this, so I'm not going to use anything.
Yeah.
But what about memory? Well, it turns out that memory just calls raw internally. So there is no optimizations for the memory domain. It's just a placeholder. So it's like, to do at the actual optimization.
Yes, as an exercise to the reader.
Exactly. Until today, where we are replacing this whole shenanigans with memmalloc. So It was never implemented. Oh no.
Yeah, well, we're gonna talk about memalloc and at a probably separate episode because that thing is fascinating in its own right.
Right.
When you are allocating memory and whatnot, like where does it come from and why is that faster than regular malloc and so on? So, in large part, that comes from how this memory is organized, and it's organized essentially more or less in 3 levels. So first of all, like the chunk of memory that like you can get from pymalloc is called a block.
Like in Minecraft.
Yes. So even if you ask for like 2 bytes or whatnot, like you're not gonna get that. Like you're gonna get like a block or multiples of a block, and it's essentially a chunk of memory of a certain size. Each one can keep only one Python object of a fixed size. So the size of the block can vary. Like we can have either 8 bytes or 512 bytes, and it must be a multiple of 8.
Why 8 cookies? Why 8?
Oh, like because we need to align our pointers, right? So like we use 8-byte alignment.
Yeah, remember this because this is going to become important in the future of this podcast when we talk about like we got this wrong.
Right. Yes. So for convenience, those blocks are grouped in 64 size classes. There's a table that I could list you now, but it won't translate well to audio. Like all you need to know is that there's 64 size classes for this, but blocks are tiny. They're not really convenient to think about, like especially that there's going to be a ton of allocations and that are going to be short-lived, right? We already know this. So we have those things called pools that are like 4K of the same kind of block. Right? And like those blocks are, as I said, like up until 512 bytes big. We already said if you need any more, then you're going to just ask the regular system allocator. So the pools are sort of smart because you have like this 4K block and there's a register called a pool table on it that keeps track of how many pools and what they do in an arena. We're going to talk about this in a second. And another register keeps track of which blocks are free.
Right.
So obviously, if you have a pool and it's all used up, like you cannot really, it's no point looking for any free space on it. And if it's entirely empty, you can also just optimize it and not look at all. Like you can just know that this is free memory that is pristine. So there's special cases for those pools that are entirely full and entirely empty. And pools even maintain a doubly linked list to the next and previous pool of the same class. So even if you actually need more memory to allocate, like there's a shortcut, don't need to go through the arena. You can just go through the doubly linked list.
This is an important detail, right? Because like one of the keys here is that we want this to be really fast. So if you just have like the chunks, like imagine that we have like one of these mem map gigantic blocks, and then we have only the small blocks. Like finding, like you cannot just say, oh, I need imagine that the application says, oh, I need a block of size 1 and then 3 of size 2. And then like if you start allocating those chunks one after the other, then like, you start freeing them and reusing them, it's going to become really difficult because there is no structure there. So the pools is what gives you like the key. You mentioned this, but it's important to highlight is that the pool contains blocks of the same size. So if you have, for instance, the pool 1 contains all the blocks of size class 1, that is 8 bytes, for instance. So it means that if an application asks you for, I don't know, like 7 bytes, then you are going to go to the pool of blocks of 8 bytes. Like you don't need to like find in the whole sea of blocks, which is the one that you want. You can like go to this higher structure, almost like a library, right? Like you don't need to scan every single book in the library to find where it is.
Yeah.
You go to the sections, where it tells you like alphabetical order or whatever is the organization, and it tells you which is the particular stand when your book will be, right? So that's the smarter thing.
Right. And finally, I already mentioned this name a few times, like we have a larger unit of pools, which is called an arena. And that's a chunk of 256 kilobytes of memory allocated on the heap. And, you have 64 pools in one. This is allocated against the system heap with a map.
Right.
So like that's where pymalloc actually does the allocation in those larger chunks, so it doesn't have to go and ask about those system calls all the time, which can be fast, can be slow. You don't really know. They're unpredictable because malloc has some complexity within. So instead, we allocate arenas and then subdivide them in pools which contain blocks.
Right.
That's how pymalloc is essentially organized. Now you know everything.
And well, there is an interesting consequence that a lot of like listeners probably are not aware, which is that the only thing that can be allocated or deallocated is the arena, which means that we can only free the arena if all the pools are free, which means that the pool needs all the blocks free. Which this means
Yes.
that if you have a single block in the arena that is being used, we cannot get rid of the entire 256K of memory, which is important. So having a smart algorithm that is able to find and free memory from different arenas and pools and blocks, like in a smart way, will allow what we call memory fragmentation. When like you have a little memory usage, maybe like 4 or 5 blocks, well, probably more than that, but like 4 or 5 blocks, but like is in 4 or 5 arenas. So like you're using 256 times the number of blocks instead of just the memory that you need. So that's quite bad. So that's why all this structure helps. And it's not only about being fast and finding a block that you need very, very quickly. It's also that to allow us to like be smart about like where to place memory. So when you free it, it doesn't hold the whole world.
But Pablo, like I heard that actually allocating memory isn't that expensive. Like you can do this rather cheaply with malloc. But what is expensive is free memory.
Exactly.
So what is that about?
Well, actually, that's an interesting realization. Like malloc is normally quite fast because like it normally says, okay, I need maybe a block of 8 bytes, and then normally it just goes directly to the size class, like the pool of 8 like blocks of size 8, and the pool immediately has a pointer to the next block, so it's literally 2 pointers. It's like here it is, bump. The worst case will be, which will be very rare, is that all the pools are full. So you need a new arena, and then you need to chunk the arena in a new pool, and then from the new pool you get a point. And even if in that case it's like 3 or 4 pointers more, so like not a lot of like computation. But free is quite annoying because free, first you need to know where is the pool that belongs to that particular block. So the block needs to more or less like be able to find the pool. So you could say, well, we could like track the information or where the pool is in the block, but that means that every time you allocate a new block, you need more data that you need to hold in the block, which means that you need more memory. So that is bad because like it means that allocating 8 bytes is going to require like maybe 16 like, instead of 8. So that's kind of not great. So there is this like computation that happens to find out what is the pool, and then if the pool is free, then it needs to like put the object in the linked list and fix the linked list. And if all the pool, like all the memory blocks of that particular pool are free, then it needs to figure out and free the entire arena, because like that's when you say to the OS, well, I don't need this arena anymore.
Yeah.
So free not only has this particular problem, but it needs to do all this bookkeeping. But it's when you need to figure out that you need to free things around, and that's like not easy. Another interesting thing about free is that because we have this kind of like, you remember you mentioned that you said, we have this like system allocator for objects that are big, that the minimum size, which is 512 bytes.
Right.
And then we have pymalloc.
Sure.
But when a user wants to free an object, it just calls pyobject free or pymalloc free or pymem free, right?
Yes.
So how do we know if the object it comes from the system allocator or it comes from Python malloc? So for that, we used to have one of the worst functions in that file. It was called address in range, and it was disgusting. It was disgusting. It does a bunch of weird shit. And one of the weird shit that it does is that it touches things that malloc thinks is free memory. Because sometimes, like if the object belongs to malloc or something like that, it needs to like figure out if the pointer is in the kind of like arenas of pymalloc, and if it's not, it needs to call free, the real free, not pymalloc free. But if it's something that pymalloc manages, then it doesn't call free. It calls malloc. So all this kind of computation, unfortunately, it cannot be done like by comparing addresses. You need to like go into the arenas and like kind of compare the different ranges of the arenas and things like that. And that is borderline the undefined behaviors, like just a bit of undefined behavior, but like good enough, like and like all the sanitizers complain about it, like Valgrind complains about it, memory sanitizer complains about it, thread sanitizer.
Yeah, so you have to disable this.
Yes, so you go to the code, you will see that there is like at the beginning of the function, there is this like very scary markers that says no sanitize thread, no sanitize memory, no sanitize address.
Right.
And if you go to these macros and then you expand them, you will find like the macro is maybe 30 lines of code, because you need like one for Clang, one for GCC, one for like the other, like MSBC, like so every compiler has its own version of shutting it down. So it's just a fucking ginormous code to say like, man, I know what I'm talking about, just leave me alone. So Nail, our good friend Nail, that works a lot on these areas, he had a very good idea. So instead of like using this unsanitized function, he created this cool idea in back 37211, which is the idea of using like a radix tree. So it's basically like a tree of addresses that you can consult. Basically like a smart phone book.
Yeah.
When you can basically very quickly using like this data structure called a radix tree, you can very quickly know if this particular pointer is in one of the arenas without having to scan all the arenas. So it's a very efficient way, but the best thing is that it's not undefined behavior, because you are just reading the memory address. You're not like inspecting the pointer instead. Because if you go to that addressing range, you will start seeing things that will scare a C programmer, Because if you're reading C code, it's like walking through the park sometimes, and then suddenly you see like an entire pile of hot garbage burning, and that's when you read volatile uint star. Some shit is happening here. Why volatile? So yes, so the compiler doesn't optimize the rates. So that's bad. So we added this like better version of addressing range, I think, to 310. And since then, that's the one that we have been using.
Yeah, really cool. And that's faster and less undefined, which I guess is always good.
Yeah.
But I guess people who are listening to us now, they're not going to be like, yeah, cool, like I'm very excited to use this feature. But in fact, like there are a few features of memory allocation in Python that you could be using. And the weirdest one that you probably never thought about is that you can actually just replace the allocator in Python entirely by using an environment variable. You can set the memory allocator on the command line just by saying all uppercase Python malloc equals, and just giving it some value. Like default is going to be whatever is default for your Python build. We're going to talk about this in a second. Then you can say malloc, which essentially means don't do any pymalloc magic, just use malloc for everything. And you can observe how terrible that is for any
not great,
non-trivial Python program. Like it's sort of a little useful when you want to actually just, I don't know, S-trace your program and like have less magic there and just see like, okay, I'm actually calling malloc here, malloc there. But you wouldn't want to do that. Like it's ridiculously slow. So pymalloc is essentially saying, okay, let's use the pymalloc allocator. That is actually not the same as default, as you're gonna see in a minute. But there's also another one that is new and added mostly for free threading, which is called memalloc. And that is sort of, I don't know, the next generation. Maybe at some point we're gonna get rid of pymalloc entirely, but that's like the evolution of CPI and so on. So we'll talk about this later. But we are talking about default. That actually doesn't really mean pymalloc. And the reason why is that maybe you compiled Python with some debug mode, which we do as CPython core developers quite a lot. If you do that, then pymalloc grows a super cool feature that is useful more often than we would care to admit, which is that it will mark memory that it gives you, and it will mark memory that it takes away from you, which sets all the free memory to like CD, 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 which essentially just stands for clean. So like that's clean memory, you got it. So you can actually observe this if you're looking at memory, whether what you got is actually still clean to use or whether you're writing over something that is not ready-made for you. But when you're freeing memory, you're going to see all of this set to DD, which is essentially means like dead memory. You shouldn't be using this at all. So that's pretty cool. But there's even another type, which is forbidden memory. So that's FD. And those are actually for data that is like unlikely to be valid addresses. So all of this is very useful because very often, like when you actually get some sort of memory segmentation faults or other corruption problems with memory, because what you need to understand is like from the perspective of the system memory allocator, very likely all this memory that we are dealing with from CPython is allocated. It's fine. You can do whatever you want with it. It's memory that the system allocator gave you in large quantities. So it really is up to CPython to interpret it correctly and to make all the pointers point at the right places and not point at the wrong places.
Which doesn't happen all the time.
Right, which is when the CDs, DDs, and FDs come very handy because you can clearly have the allocator help you figure out that like, oh, you wrote too many bytes there, like, and you're overriding now something that you shouldn't
One parenthesis from the blue. Do you know what notebook LLM is?
Notebook LLM?
Yes, I swear that it is related to what you just said. So Notebook LLM is this project from Google DeepMind when they released this tool that now is probably the most popular tool that uses Gemini. When you can upload like a PDF or like a web page or something like that, and you can kind of like talk with it like any other bullshit LLM. But one of the cool features that they added is that you can generate a podcast out of that shit. And then you will have these two people like talking about it, like, and it's very impressive, like how it resembles a podcast. But, the same thing with all this LLM thing is like very quickly you start seeing the Sims. Like you notice the patterns and then you start like, okay, this is bullshit. So one of the things that they do here is that they abuse this kind of podcast-like thing when some of the hosts say something smart, like you just said, and the other as the metaphor for stupid people. So you said like, it's adding this clean byte and dead byte. And then if I'm the other LLM host, I would say, wow, it's like creating clues for a detective story. So, like literally this all the fucking time, all the time. It's very cool to see how they create these metaphors. Like, for instance, I tried one with this what's new in Python 3.13 and it was talking about PyREPL and it's like, all those pesky error messages, you can use this multi-line history. Oh, wow, it's like having all the possible like editing capabilities, like having an IDE at your fingertips.
Wait, I'm no longer listening because all I could hear is that you were already generating episodes of the podcast without me in them.
You fracking snitch!
You just want to replace me with an LLM? Like, is that what you're trying to do? What is happening
You're the
there?
smart person. I'm just learning how to do the metaphors for stupid people, which is my function in this podcast. You're the smart guy.
Spanish drama. Oh no.
Cancel project. He find out.
Oh no.
Oh, okay. So yes, this is like creating clues for your detective story, Łukasz. Like so now you can know if the memory was corrupted because nobody filled it up, that's clean byte, or because someone messed with it, like messed with the clues, that's dead byte, or because someone touched some memory that is shouldn't, that's forbidden byte. Like for instance, buffer overflow or something like that.
Yeah. So how is that useful then? Like what do we use that for?
Well, all the time. Every time we screw up, then this yells at you, like. Because you just don't get segmentation fault. You get like memory, and then you get this. It's super cool because when you show this to someone which is like not used to this kind of low level debugging, it shows this kind of like dump of the memory, and it shows you like these letters like DD, FF, blah 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 blah, and it looks like the most hacker shit on the planet. Like you look at that matrix of letters, and then you say, "Oh, what happened is." Explanation, and it looks like you're fucking Sherlock Holmes, man. Like this series from the BBC when like Sherlock Holmes was having this hyperspace vision when he could like see everything that happened backwards. So that's what you get, and then you look at these letters and then you say, okay, so what happened is that this other thread like was modifying things and it was thinking that it was a bigger structure and blah blah, and people freak out, man, because you're just doing this by looking at letters. So this is why it's useful. It's useful because you can look at letters and you can tell what happens. is very cool.
You're saying Sherlock Holmes because you're already kind of, immersed in your British culture in London. Like all I could think about was like Cypher in The Matrix saying like, I don't even see the code. All I see is blonde brunette, right? Like this sort of thing.
Blonde brunette, but it kills you.
So that was my culture seeing actually what's in that memory and whatnot.
Okay,
and you're like, oh, Sherlock Holmes. Like, yeah, you could really be that LLM buddy for a podcast.
But isn't in that scene in The Matrix? Isn't the blonde like just turns out the character and kills them or something like that? And that's when they go to the Matrix.
The red dress woman.
Yeah, that's it.
Yeah, that's a different scene, but yes, exactly.
Okay.
I've seen that movie too many times, way too many times.
Okay, makes sense. Well, one of the things that this does as well is that it doesn't like only do this, like, kind of fill and prefill the memory, and when it frees, it puts the extra bytes. Is that it actually allocates double size. So if you are asking for like 8 bytes, it allocates 16. And basically, it adds memory on each side of the actual block. And the idea is that it will use this extra side on the sides as a forbidden kind of section. So it will know you're writing past the memory that you are using. For instance, that's very useful.
On the both ends, actually.
Exactly. So this is very useful. For instance, let's imagine you have an array, and then you have someone who is like an array of size 3, and then you have someone writing at the input fourth of the array, because C
legal language
doesn't have bound checking, and then not like Rust or something, the legal language, the very legal language. So like C doesn't have bound checking, then you will know that you are writing outside the array. Otherwise, if you don't do this, well, guess what? What can be after my memory block, Łukasz?
Well, there's going to be another one, right?
Someone else's memory block. It could even be yours. And then I will be writing inside that memory block like a bad neighbor. And then I'm fucking something else. And then like that something else blows up. And it doesn't have anything to be with the thing that you were writing to. So imagine that
it would not be that bad if that was actually a different processes one, because like that's easier to discover. But if that's still Python's, then you're just corrupting your own memory, and it's super bad.
So dear listeners, this is a true story. This happens to every single one of us that don't use the debug mode, because you will say, but you have the debug mode, why you don't use it? Because it's
slow.
It's very slow. So some of us that have been here forever, we said, I don't need these like, bicycle wheels. I can fly like the big boys. And then bada boom, bam, boom, like explodes in your fucking face. And not great. So this is something that we have experienced. You, let's say you are like, I don't know, some Spaniard person with an unidentified origin, and then you are smart enough, and then you decide to write to like entry 4 of an array of size 3, because that's what you do on Saturdays. And then what happens? And then nothing happens. You just write to that array. And then 2 hours after that, because the program has been calculating some shit, then it prints the dictionary, and it blows up, because it's not a dictionary anymore, it's now the number 6. So the number 6 is not a dictionary, and it will try to read it will blow up. But that happens a lot of time afterwards. So it's very difficult to know what the hell happened. You need this like extra cool technology like the reverse debugger and all that shit. But if you just compile it on debug mode like everybody should do, then immediately it will complain and say,
not super immediately, which sometimes makes the debugging like not like very obvious, like what you did wrong. Like you're gonna be able to debug at some point because like what the changes that you're making are. But if you're looking at some like older bug, like it might not be like immediately pointing you at the problem, because when it discovers that the forbidden bytes are overwritten, it's when you're reallocating or freeing memory. So unless you do that, then like you're not gonna see that those are actually overwritten, right?
Right. Well, maybe not immediately.
Yeah. So like close enough, but like I had situations where like the output was somewhat misleading to me. You need to be a little bit of a smart Sherlock.
Okay, can we agree? Can we agree that then activating debug mode it gives you a Watson?
It
gives you a Watson. Doesn't solve the mystery, but like it gives you a Watson.
Yeah, I mean, like in the TV series, Watson was actually sort of like a very important component. Like you could clearly see that Sherlock without Watson would just not be successful.
Right, exactly. No. That's the whole point. Like it's the person who actually does the groundwork, and Sherlock just looks at the matrix. Yeah, okay. I mean, we have bigger tools than this, right? Like we have big guns that we can deploy here to actually tell you immediately when you screwed up, but that requires like big boys, like sanitizers and things like that, which is not super hard. Like it sounds harder than it is, but
Yeah, but before we get to that, since we're already talking about special values and so on, like you mentioned before that we use 8-byte alignment, but not really. But tell the story.
Exactly. This is very interesting. And the big twist of the story is that I have already told this story on the podcast. It was we talked this in integration event, chapter 14 or 13 of the podcast. So what was happening here is that we used to align all these blocks to 8 bytes. That was the smaller thing that could happen, right? So we return pointers that the addresses are aligned to 8 bytes. But turns out that most compilers, at least in like x86 and 64 bits as well, like assume that the pointers that the allocators return will always be aligned to 16 bytes. And it used to be that, it was 8, but that was long ago, and now it's 16. And which means that sometimes when you get like one of these like pointers from malloc, the compiler starts doing some weird shit. But very in rare cases, when it assumes that it has a pointer to 16 bytes, but it's only 8, and then weird stuff happens. So we discovered this actually quite a long time ago in 2016, and then we patched. That was around Python 3.7. Jesus, man, 2016 was Python 3.7.
Yes,
the world is a weird place.
Yeah.
So now we changed pymalloc to also return 16-byte addresses. I think it was a change by InternalDocs, which is the GC head and all that stuff needs to be also bigger because that needs to be aligned to 16 bytes. So that was the big bug that we solved. And I talk about this because in Bloomberg, this blew up in the future when GCC became a very smart compiler and started to say, hey, it would be a pity if I grab this 8 align pointer and I try to use an AVX instruction over it. No. Eventually, if a bug can happen, it will happen in 64 bits. I think in 32, we still have the restriction of 8. But, who uses 34 bits? No one. Anyway, moving on. Sorry, don't.
So just today I saw that we're still using it in a few places. But let's talk about this.
Yes, all people like 32 bits because it's smaller. Well, Windows actually is quite popular. 32 bits still. Do you know what is the wallpaper engine? You know wallpaper engine? What it is? It's a very popular program among gamers.
Yeah.
To have animated wallpapers on Windows.
Oh, my son has this.
Yes.
Okay, so that must be that.
Yes,
then.
yes.
Okay.
It's in Steam. So when you launch, even today, when you launch the wallpaper engine, it asks you, do you want 32 bits or the 64? And it says 32 bits uses less RAM. And
because alignment,
it's important. So if wallpaper engine is using Python, then it's using 8-byte align pointers. Not great.
All right, so now let's actually talk about ways in which you can help the end user in that particular weird world of allocating memory. And I'm going to start with something very weird, which is something that I fell in love with, which is, I don't know, is that on topic for this podcast? Maybe yes, maybe not.
Love is always a topic.
So we have this thing on PyPI because it's not maintained by us called Python.
Yes.
And what people use this for is to write C extensions that are firstly correct, because it's much easier to write in Python than in raw C, the illegal language.
The illegal language.
Right. But also it can be way more performant, right, than raw Python, because it will actually skip the interpreter loop and so on and so on. But did you know that you can just write C with Python? You can just skip all of this Python stuff there and just write C but using Python. And this actually allows you to use a very cool sub package that you can get from PyPI called cymem. And cymem has this concept like automatic memory management only for C, which is a pool object. So if you create this pool object somewhere and you can just put them as attributes on objects, and you can put them in functions as sort of internal data, as locals to a function, and so on, then any memory that you're allocating with this, you don't have to care about deallocating, because it's going to deallocate itself when that object is destroyed. And this is super cool in terms of how automatic it is. So it allows you to actually have heap allocating memory, sort of kind of like what you can get in C++, only without C++.
Yeah, well, except that distraction in Python is not guaranteed. So kind of like,
Well, but what I'm saying is like this allows you to actually just write pure C. It's like you can literally just skip the part of the I don't know, like of the Python API there. But even if you have the Python API, what can happen then is if the destruction is not really that deterministic, is you're gonna have a memory leak. Not great.
No
Yes, so
bueno.
you're gonna still have to debug this. Suboptimal.
Yeah,
But
not
do we
great.
have anything for our users that don't use cymem, don't use Python? They just use Python to actually hunt for memory leaks and see where the memory goes? Like, what can we do?
Well, it depends. Like any senior engineer will say, it depends. In Python, thanks to our good friend Victor Ristinir,
Yes.
he added in PEP 445. Man, we are now around PEP 700 and 600 something. So 445 looks like ancient.
That's 454.
Yes, 445. No, okay. No. That you're talking about tracemalloc because he added in first he added a scaffolding for this in PEP 445. Add new APIs to customize.
Look, so he had like all the cool
All the
numbers.
peps, all the peps are Victor Ristinir. So Victor added first the possibility to override the Python allocator. So you don't think pymalloc is good? Now you can have your own. Well, you can construct your own and then you can hook it. And so you call this new thing called pymem sim allocator, which has kind of a non-ergonomic API, let's say, and then you can do all sorts of things. So you can have your own like mega malloc if you want. Nobody does this, but what people do is wrap the allocator. So it actually calls whatever allocator was set there, but it does something before, and that's how you get these tools. How do you use leak checkers and like memory profilers. And in Python, now, yes, Łukasz, now is the time. Victor, in PEP 454, he added tracemalloc. Wow.
Yeah.
What is tracemalloc?
Well, it allows you to see who wanted more memory. So you can see that there was some memory that was allocated and where from. But you see that some memory was, but you don't really see what objects are there. Like you actually only trace memory blocks.
Yes, this is kind of good because indeed, if you have a leak, you can see where the leak was done at the Python level. So normally, and this is kind of a like problem. Like, I mean, it's very useful, but like sometimes it's like most of the time you are going to have a bigger brother. We will say the name later. But like the problem here is that if you have a leak in a C extension or one of your Python shenanigans, then it's going to tell you, well, you have this in a function called run. And then, there's C code underneath, but, tracemalloc cannot know that. So it says, yep, run. And even if you know that, that some blocks were leaked, it won't tell you exactly what objects. It has a bunch of things that are cool, though. Like, for instance, if you run like tracemalloc, and then, for instance, you have an object yourself, so it won't tell you which ones, but let's say you have one, and it was allocated during the tracemalloc scan, you can ask tracemalloc, hey, man, where was this object allocated? And this is actually used very heavily in the CPython debug mode.
Yes.
For instance, if you forget to close files. Because like you run under tracemalloc, and then when we discover when the file is deleted that, hey, this should have been used as a context manager. Like, what is this going on? You can pass this pointer to tracemalloc and ask tracemalloc, hey, where was this file created? And then it tells tracemalloc, say, okay, this file was created here. And then you can point and say, hey, guy, like or girl, like you forgot to call like the context manager over this thing here. And it does the same thing for a lot of stuff like sockets. And coroutines, for instance. If you never await coroutines, then the destructor of the coroutine will know that it was never awaited, and it can tell you, tracemalloc, that you forgot to await a coroutine, which is a very common mistake.
Coroutines are actually interesting because for the ones that you're gonna have inside function calls, you might learn quicker than later that coroutine never awaited on. You're gonna see this warning appear, but for some, you're only going to see this at the shutdown of the program, which is super late.
Right.
So being able to debug this, very helpful.
Exactly. But unfortunately, it only deals with Python memory. So, for instance, and you can opt in into, like, for instance, NumPy doesn't use Python memory, but it can tell tracemalloc, hey, I have this big NumPy array, so like you can still use it. But if you use some other library like SciPy and things like that, those don't opt in, or they cannot, or they're using some libraries like Blast or OpenBlast and things like that they don't know about tracemalloc at all, and tracemalloc won't see this. So tracemalloc is just a partial view of what's going on, only in the Python side. If you want the bigger guns, then you need other profilers. Like which one, Łukasz?
Like I had a friend who was into that stuff, and he was maintaining what was it called? It was like this like science fiction name. Like it was like mem and like some like
the Matrix,
mem lightsaber or something like that. I don't know. Like memray.
Memray. Wow, memray. You said that. Yes. Big boy profiler, or big girl profiler, like both. We accept everything. So memray is a third-party tool that I maintain partially in my work, but because I'm very into profilers. And this is like tracemalloc, but on steroids. It will allow you to trace absolutely every single thing on the planet. And it works on many cases, and you can get like pretty plots and like a lot of cool stuff. It can tell you about leaks and a bunch of things, and spam. So check out memray today.
Yeah, you should. Essentially, it's more advanced way to do the same thing, which I think we should do all the time. I am hurting inside ever since we lost the original videos from pyvideo.org.
Pyvideo.
It's still there, but it used to actually host videos from conferences as well. But like some single person was paying for that hosting the entire time, and then they were like, hey, I need some funding. They didn't find funding in time, so they literally just deleted the videos.
No.
It was very sad. It was very sad. So we lost, for example, like very old conferences like EuroPython from 2009 and in 2010. And there was this amazing lightning talk. If you're listening to us today, like, please contact me. You will know what this is about. There was this lightning talk that was about how you shouldn't code like an ultravillain.
What?
Because in every Bond movie, you have this ultravillain that is set up for success.
Ultravillain.
He has everything that he needs to kill James Bond. But usually, he just waits too long.
Because he's telling the evil plan or something to
Yes, he's just like spending time like chasing James Bond with a gun, but he has this big like, kind of atomic thing or whatever, or something that can evaporate like everything.
Right.
But no, he's not going to use the most sort of powerful weapon. He instead goes for some like silly weapons that obviously James Bond is better at using. So this entire sort of this entire lightning talk was about how you shouldn't do that. You should start with the most powerful weapon that you have, with the most powerful tools from the start, because this is way better. And it gave many examples about like print debugging versus real debuggers and whatnot. And like memory profiling is something that like, even if you don't really have much trouble right now, you can run this to just see what your process is doing, and I can guarantee you'll discover something fun.
Well, this happens all the time. Like, do you know that I did this experiment, like a non-ultravillain. I still would like to be an ultravillain. I'm conflicted about this, but like, okay, so I actually did this over like CPYTHON, like the smaller thing. I think like some foo function, but turns out that foo function was annotated. And then the annotations at the time import typing.py. And using that, I discovered a bug that was 20 years old there, like a memory leak that was happened, and it was being triggered by the like instance with like mega overloaded meta classes, blah 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 blah. Like, like it's very rare, but it turns out that typing.py, I don't know. I mean, obviously you are a typing connoisseur, so you have clearly looked at typing.py. But dear listeners, if you want to be on a maze of little passages and be lost, just open typing.py on CPython and cry. All the things are used there. Like every single thing. Because typing.py is like the Bond ultravillain, but like for real. Like it will use the tools. Do you want meta classes? Of course, we have meta classes or meta classes and like weird things that register themselves in other places to lie about the things that they are, and like then they plus like blah 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 blah. It's like crazy. And among all that madness, it was like at least 3 memory bugs, man. Like wow, one of them like 20 years old, the rest like 1 or 2. So yes. It's there is only one problem. It's like, oh, Pablo, but you're that smart. Why you don't use memray all the time with CPython? Well, guess what? Because new versions of Python change the Python C API and they break memray. So we need to upgrade it for every single version, which means that it works for 3.13 now, but it doesn't work for 3.14 because like, it needs to be upgraded. So we can only use it for like actual Pythons that have been released, and we cannot use it for development.
But okay, like, who can use memray? What operating systems can you use it on?
The non-Windows operating systems. Everything except Windows. Because Windows makes the evil darkness tricks that memray uses very difficult. And I'm not a Windows programmer, so I don't want to invest on that. I know it's possible, but I don't want to do it. Like memray does a bunch of like crazy things, like rewriting the assembly code of the program on the fly and a bunch of things. So that's kind of like hard to maintain.
Right.
Literally, you know what happened? So I'm dear listeners, I lost my computer yesterday. Like my cool bro water cooling actually leaked and destroyed my GPU.
True story.
Yeah. It was not super new. It was a 2080 Ti. It's insane how these things depreciated in value. So my computer died. Oh no. I'm not using water cooling anymore, but I switched to this M1 like Mac Mini that I have here for running buildbots at home, and I upgraded to macOS Sequoia, macOS 15. And then as I finished this, I said like, let me try memray on macOS Sequoia because Apple likes to break shit all the time. And of course, it broke memray yet again. Do you know why?
I'm not sure what they did this time.
So
No.
so Apple had this great idea to have the linker cache. So they say, oh man, like there is all these like libraries that are loaded all the stupid time. Like,
Oh, so I know about that. That was added in Ventura.
let's just create a ball of fucking mad and like just a
Yes.
gigantic fucking ball and like let's lie about the linker will lie.
Yeah, that they live on the file system, but they don't.
Exactly.
Yes.
So it's like phantom thing. Okay. But now that they have this, because they are not real libraries that are on the file system, and they are only in the ether, then they can do all sorts of weird, incompatible shit because the linker will lie about it. You know, one of the things that they did, they changed the name of malloc.
What?
Yes. So macOS Sequoia internally doesn't use malloc anymore, not realloc, not calloc. Do you know how they are called now internally?
Oh, with Apple? I don't know.
They are called malloc underscore type malloc, and then malloc underscore type realloc, and malloc underscore type calloc.
But why?
I don't know, man. It's just there are stupid people that like to break things all the time. So if you are listening, dear Apple employees, I know you are listening. We know because we met you in PyCon. You are great people, but go to the linker team and tell those guys not to break the memory allocator people by changing malloc all the time. Don't break the memory allocator people. Malloc type malloc. If you go to memray right now, there is a PR that basically fixes this by removing this type whatever from the name of the thing. Yeah, not great.
Yeah. So when you said like, hey, they must have renamed it. Like, my first thought was really like, all of their actual APIs that they had in Objective-C and whatnot, that came from Next, right? Like that's where macOS 10 initially came from. So a lot of APIs were like NS something, right? Like NS object, NS whatever.
This is, I think this is because checking the section of the Mac file where this lies out, because you know that there is a secret trick to actually decompress those files from the void, and you can bring them back to disk and then inspect them. So if you do this, you can actually check where the sections are and whatnot. And these are in a section called auth stubs. So there is some security shenanigans going on there.
Oh,
well, in any
okay.
case, do you know how you can observe this yourself at home and run this beautiful experiment?
How?
Because this is not the external interface. Like malloc still exists, obviously, because they're not going to break every C program on existence, right? Like malloc still is a thing. It's just the internal calls. So you know how you can invoke one of these internal calls?
I don't know.
By using C++ and creating a vector. So you C++, you create a vector, and then you never call malloc. The vector, bloop, is created on existence. It uses internally new.
Right.
And new in C++ uses malloc, but it's never exposed. So those are the ones that are renamed. So if you want to like run this experiment at home, create a program in C++ that creates a big vector and pushes a bunch of elements on the vector and prints something just to the compiler doesn't optimize, and then run this under a debugger and put a breakpoint in malloc. And you will see that the breakpoint is never hit. And now put a breakpoint in malloc underscore type underscore malloc. And then voila, the breakpoint now is hit.
Fantastic.
I'm
not running Sequoia yet. I learned a long while back. I was actually in line for macOS 10.5. What was that? Leopard, I think. Yeah. Wow, this is going to be amazing. And it was like buggy, but it was pretty cool. I loved it. It was great. Snow Leopard made it even better. So I kept like upgrading on day one, and upgrading on day one to 10.7 Lion bricked my computer. The reason why, the reason why was I was using File Vault, which was at the time the way to encrypt your home directory. You couldn't encrypt entire drives yet. You could encrypt your home directory. But something changed during the update, and it made macOS unable to actually decrypt your home directory. Dun, dun, dun.
Oh, no.
Yeah, that was not great. In the end, I found ways to actually get everything running again. I no longer remember what I had to do, but now I have enough computers at home that this is not so stressful anymore. But at the time, let me tell you, it was not what I needed.
Right.
That was a very stressful few days.
Well,
so,
I mean,
I no longer upgrade on day one.
I feel you. I mean, remember the original of the story. I lost my PC and my graphics card, and then I went to this other computer and I learned that memray is broken on the new system, so it was not a great day. But don't upgrade to macOS. It just brings pain.
What is this podcast about actually?
Just two dudes complaining about stuff.
It's about Python, isn't it?
Okay. Well, but now in 3.13, memray is going to use this like tracemalloc machinery to do something that only tracemalloc could do, but now after 3.13, tools can do as well, which is that it cannot only trace memory blocks, it can trace actual object creation. So this is big deal, man. Do you know why it's big deal? Because now memray will tell you leak this object here. And because memray can tell you the C code when this happened, it will tell you exactly where is the leak. So you don't need to run ref leaks anymore. You can just say here.
That's fantastic.
Like this is the thing that you leak is here. And it will give you the traceback and what Python functions, because like memray does hybrid tracebacks.
Okay. And on that positive note, let's talk about right. So maybe let me start for this just for a second, because I have like the weirdest PR that I've been spending some time on.
I have the weirdest PR as well. You first.
We'll see, because both of those are really important for us core Python developers. And none of those are actually any CPython features or bug fixes, but we wanted to share with you some other sort of shade of core development and what that sometimes entails and means. In my case, I had this very motivated person from ARM.
Hey, Diego.
And he's like, hey, we want to run ARM GitHub action runners. We want actually for Python to use them so that you see when stuff gets super slow or it just doesn't work on ARM correctly. So how about you use them? There is now a way to use those ARM runners on GitHub. We quickly discovered that yes, but it's paid. So there were some shenanigans on like, how are we gonna make it so that we don't go bankrupt in the world of premium GitHub action runners, which can get expensive really quickly. We solved that, that's fine. But then we actually had to enable this. And as of today, we are in the process of doing this. But it was way more sort of involved than I would expect. So what you want to do is to make some of the jobs that we already had, which, for example, was an Ubuntu job.
Right.
And we were running 2204 on x86. And you want now double those jobs to also run on AArch64. So what could be easier, right? There is a .github directory in our source code. There's workflows there. Some of them are reusable, so it should be very easy to set all of this up. And it should be running like that. It should be very easy.
No.
Well, yes. So all of this is in YAML. And YAML is sort of a weird format on its own because, for lists you can
say it's crap. I think it's
so
acceptable.
like I am very ambivalent about it because plenty of its decisions are clearly suboptimal, but at the same time I sort of like the colon and I like the indentation in it because it's cleaner to read. But then you're faced with the fact that like you have a list and that list can either use square brackets or it can use like the dash sort of separated lines. But if you indent them wrong, then it means something else.
Yeah, it's very
and
annoying.
So on and so on.
Actually, I'm looking at your PR and I like how the commit messages tell a story. So the commit message says, remove unnecessary lim mpdeck. Bump to see how large your build does. Just say J. I suppose because you changed minus J4 to J or something.
Yes.
See if Windows works. Apparently it doesn't work because the next comment is substitute true by true.
Yes.
Try a different approach with Windows. It clearly didn't work. And then the next comment is YAML.
Yes, YAML.
Exactly. Let's see if that works.
Yeah, and it continues like with YAML being weird because not only YAML is weird, right? Which everybody knows the story how about like when you say yes and no, suddenly no is treated as something else. So if you list countries, like you're gonna have PL for Poland and that's fine, but no suddenly is false, right? And so it's like everybody knows the story. But on top of YAML, you also have GitHub YAML, which essentially on GitHub Actions requires you to do things in a particular way so that you can pass data between different parts of the config. So you have the matrix where you can define some attributes that later on are just automatically sort of multiplied. So you have this entire matrix of computation that you need. If you do it not exactly how GitHub wants it, your matrix is going to be empty. You're not going to see any error appear. If you actually can see that you made a syntax error and you can look at your GitHub Actions, there was a problem, that's fine. But if your matrix is just empty, all of this was pretty weird. Linux was solved. Oh, and the J story and the lib mpdeck story, like all of those are fun because mpdeck is what we are using for decimal.
Right.
It's the accelerator library. It's the C library that implements some of what decimal is doing internally. And that used to be part of Ubuntu. But now in 2404, which is what the ARM runners actually provide you, that's no longer provided because it's an unmaintained library. At least that's what the Debian people are saying. Like I'm just saying
implications.
So I was like, oh no, what should we do? So I'm looking at how Python is now using lib mpdeck, and it turns out the only way you can use
we vendor it, no?
We do. But the only way to use a one that is on the system is literally in the configure, just saying like dash system
with system
lib mpdeck. Yeah. Yes, but we never do that. We don't do that in GitHub. So we were only adding this dependency for no reason, like all this time. So now, okay, we don't need it. That doesn't matter.
But I think we plan to remove it. So this is not a great feature for removing it. Well, I will see.
So like, okay, if we plan to remove the thing from like external dependencies, then we're going to have to solve the problem. Where do we going to get it from if it's no longer bundled in Debian?
Yeah, that's so
interesting. And changing -J4 in make to just -J is just something that like I'm not even sure why we did it originally as -J4. So if you don't know this, like if you just say make -J, it'll look at how many cores you have and just use all of them magically. So it's just...
I think it was just not to oversaturate. I mean, you normally do that so you don't like oversaturate the machine just because you want to compile Python, but in the CI it doesn't matter. Because like that's
in the CI, we are running runners that are 4 cores, and we are running make J4, which is exactly the same amount of the cores that we have.
Yeah, it's also virtual core.
Yeah, and now the ones that we are setting up is actually 16 core. Ooh. So like it runs all tests in like under 2 minutes.
That's awesome. Yeah.
Extremely quick. Like I love it. Yeah, it's great. But yeah, that was one thing. That was one thing. But then we were like, yeah, but don't you also have like now those awesome like Windows ARM runners? And that was yet another story. Like I wasted so much time on that, like that. Like,
CI is like a blood sacrifice. like it always is. Like you need to pay.
At some point, I was looking at this YAML because it looks trivial. It looks so obvious what this is doing, and yet no Windows jobs were running. Like essentially, I made a small change, and suddenly all Windows jobs disappeared. So I literally went to our Discord and and asked other people, saying like, "Hey, can you see what is going on?" And like Zach and Hugo both said like, what you're doing makes sense, but what I would try is just add this other extra line that I guess it won't hurt if you try to add it. And we added it and it works.
Wow.
So it was so weird because like, okay, I could also try to do it like that, but why? Like it doesn't say in the docs
the goals
why.
required. Is the blood sacrifice? You didn't sacrifice enough blood. Some new lines.
Yeah.
Yes.
So finally now now we are in the moment where we are running the jobs. It's fine, but the super new images for Windows on ARM forgot to include Visual Studio, so it's kind of hard to compile without the compiler. So we're waiting on that to be rectified, which should be like very soon. But in the meantime, we're gonna also add this to our JIT jobs. So as a Python user, you probably don't know this, but there are plenty of things that we only do in sort of like a compromised way, just in the interest of time. So for example, before those actual ARM runners for Windows, we couldn't just say, you know what, we don't care about ARM on Windows. We needed to build Python for ARM on Windows just to know that we didn't break the build.
Right.
Breaking the build happened more often than you would know. But how do you build for ARM if you don't have ARM? Well, you can cross-compile, right, with Visual Studio on x86. But what that means is that builds pretty slow because it's cross-compilation. So you're already paying this price. We're going to wait for this longer. But then the extra sort of gut punch there is that you could build it and you cross-compiled it. Congratulations, but now you cannot run the tests with it because you're not on the right architecture. So that was a compromise that we are now rectifying. Like ARM is going to be like a first-class citizen for us. And another case is when we have this entire JIT workflow. You might have heard about it from Justin. So he would explain to you how there's LLVM as a dependency, and that dependency only exists at build time. Well, so guess what? So the CI is that build time.
Right.
And you're creating all of those templates that you're compiling for copy and patch and so on and so on. And those jobs take a long time. So we don't run them always. We, again, run them only when we make changes around the JIT. Like there's some discovery there, whether you're touching the JIT code, and only then you run those very long jobs. And again, if we didn't have actual native ARM runners, we couldn't just give up and not do this compilation. We did do this, but using cross-compilation,
right,
which is extremely inefficient. So now we will be able to do this natively, which is going to save us time, is going to make the JIT better. So all of those things is how we spend our time. And there is not going to be a super cool PyCon talk from that, because all of this is simply just, looking at a YAML file, feeling like an idiot because you don't know.
Is there any other way to look at that YAML file, Łukasz? It's like that's how I feel all the time.
So okay, if you're doing stuff like let's recover the stack trace from a different process, just copying memory and following the pointers, like this shit is supposed to be hard. So like I can tolerate this, making me feel like...
I know, you tell me you're supposed to be doing that as well.
Yes, I'm doing that as well. Yes. We're going to talk about this more in the next episode when I'm actually done. So that is supposed to make me feel stupid, and that's fine. But a YAML file...
No, the YAML file is harder. Like, no. Kernel system calls, like assembly patching, no. YAML is the real
There
enemy.
is some documentation there, sure.
That's the big weapon of the ultravillains. Like that's the big weapon that they should use, just the YAML file.
Yeah, man.
Deploy the YAML.
Okay. I see your YAML file and I raise it to the other thing that you will feel stupid just staring at, which is my other PR. So long ago, when I was a release manager, I was full of life and happiness. And then I become a release manager. And what happened is that I said, man, like every time I need to do a release, I need to go to this buildbot page and like look at this like ginormous list of builders and find which ones are failing and which ones it will be okay if they fail and like what is the deal and like what are the main branches. It's just very boring. So I said like, man, it would be cool if we have this dashboard. Like everybody that wants dashboard. So I say I want a dashboard and like. So I created this dashboard in the buildbot page using my really crappy HTML script skills as a C programmer. And I created this dashboard. And it was actually cool because mostly I used pre-made CSS from buildbot. That was like, all cool. And it was doing all these cool like drop downs that animate dynamically. Also very slow. But well, it was so slow that, as you know from Łukasz, we needed to cache it. Because like in Brno we did this PR because it was so slow to generate that now we're caching it every 5 minutes.
Yeah, because it had like a tree of SQL statements. So like there were so many queries in that one page that it just generated for
Well, I mean, buildbot just
seconds.
goes to shit with like 10 queries. So it's not also like amazing, but yeah, different problem. They should change the language. What language are they using? Oh.
No. Actually, if you look at where like most of this waiting happens, it doesn't happen in Python. It happens on SQL.
Okay, so maybe they should change the database. Well, anyway, so I did this benchmark. But then what happened? Our friend Victor Rustini changed the version of buildbot from 3 to 4, and everything went to shit. No, so everything broke because they changed React to
Angular to React.
Angular to React.
Yes.
And
a
they
lot
say,
of JavaScript just stopped working.
these classes that were in the CSS that were part of the public API, now they are not, and now they are not there. So the thing was broke, and then Peter appeared and he kind of like fixed bare bone fixing. So he transformed the dashboard into like a broken dashboard into a non-broken dashboard. Actually with better information because he grouped everything on tiers and whatnot, but like basically no CSS. So it looked totally like a C programmer designed the stupid page. So,
as it should be.
Yes, like disgusting, all like, bleh, like all like disgusting. Everything was confusing. So I was looking at like what they have done with my boy. So I said like, maybe it's time to learn CSS. So you say like, okay, so what cool features do you plan to learn and use, Pablo? And then I answer, yes. I use all of them. I literally spent like 4 hours reading all CSS I could. And then I use every single shit I could, like advanced selectors, pseudo classes,
rounded corners,
rounded corners, CSS animation, CSS transforms, flexbox, and CSS transition, and CSS custom properties. Wow, very modern design. Really cool. I learned all about this ad media bullshit for making things responsive. And, this is very responsive. It uses this calc thing to just make a bunch of things, and panel success thing. This is just classes to create panels and change the panels dynamically. So now it's using all the CSS properties. And let me tell you something. I felt miserable doing this. I hate CSS design. Like, it's so difficult. Like, it's just so difficult. Like, you change something bad and then you don't see what you're doing, and like it misaligns. It's just so hard. Like, everyone using CSS, you are the actual heroes. So yes, but I finished. And now, if you go to the buildbot dashboard, it looks gorgeous with these like weird colors that I selected. But like, you hover over the boxes, like they raise slightly and they drop this shadow, and then there is these pills that change color when you hover over them, and when you click even different color, and when you change, it changes from red to green. Like, fantastic. It looks like a C programmer coded this, but in a different way. It's just learned all the features. Like, it's all the features. I'm going to use all the features.
Yeah, but don't go there because all the branches are red now.
Oh, no, but 312 and 313 are supposed to be green, right?
Yeah, 312 is green, so that's awesome.
Wow. Okay, so that was it. And now, my friend, it's time for...
What's going on in CPYTHON?
Right. So let's start with clapping for ourselves, and I don't know, congratulating ourselves for actually delivering on what everybody asked us for.
Self-congratulatory.
Oh yes, exactly.
we deliver.
Who else? Like, what other hosts are gonna do this for us? Unfortunately,
Exactly.
we're the only ones.
It's our podcast, so we talk about us.
Yeah. So we made this feature in Python 3.13 that well, supposedly is pretty popular, but other core developers asked us like, hey, so how did you actually design this? How did you actually come up with this? So we had to make a PEP.
And the PEP has the best name.
Yes, it's replacing the default REPL.
Why that
But
default? Default sounds
replacing-
weird. You see, you trip on default because the original name of this was replacing the REPL, right? And then you say, well, but then you went full like pedantic Łukasz. Well, it's not replacing it because there is a fallback and blah blah blah. And I said, like, okay, replacing the default REPL.
You are spending way too much energy on like cool names for PEPs.
I'm redeeming myself, man. I'm redeeming myself since I did this fine grain traceback, blah 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 blah.
Yes, so
Because
I know what you mean. At the same time, for me, names of PEPs were always supposed to be the most descriptive and boring. It's sort of like
not anymore.
in Python.
Not anymore.
In Python, we don't use any code names for like libraries. In the standard library, we use descriptive names, right? Like, and that was sort of by design. And similarly, I thought the PEPs are supposed to be boring, but then like you just show internally how cool they are and so on, and that should be fine. But okay, we have replacing the default REPL, and I insisted at the default because we're not really replacing the old one, which is solving a big problem that a lot of people like try to put on us, which is like,
I have to say
can you
something.
parse input RC, which we will never parse input RC with PyREPL. But if you really want your custom input RC, you can still use the old REPL. So did we replace it? No, it's...
I'm still happy with the stupid name. I was going to say that to your let's use boring names, I was going to use this sentence that I always wanted to use but I never could, which is tu quoque brute filling me. Do you know the sentence?
What?
That's what, yes, this is Latin, is the last, well, one of the last probably sentences that Julius Caesar told Brutus, which is
okay.
yeah, so it's like, you Brutus, my son. So because like Brutus killed Caesar, right? So Caesar felt betrayed. And so you can say in Latin, tu quoque, that's you as well, Brutus filling me, my son. And this is because you as well are impeding the fun on stuff.
Well,
I got
but it is
at
there
work.
now.
I had this project to refactor thing, and I wanted to call it Patchy Mat Fix Face, and they said no. So now it's called I don't know how it's called.
Maybe Patchy Body.
Now everybody is cutting my wings, man. Patchy Mat Fix Face, man. It was the best name. Patchy Mat Fix Face.
Yeah, well, in any case, I thought our PEP is going to be informational because that's the best
kind of PEP. Yes.
But then Pablo insisted that like no, it has to be a real PEP.
Well, some
meaning
people ask
standard
for it.
struct.
People ask for it. I think it should be informational because it's the best kind of PEP.
And now it is informational again. Like during the review stage, essentially it was reverted back to informational. So in the end, sanity prevailed.
All roads lead to Rome. Whoa!
Yes, exactly. Amazing.
Combo from Pablo. Okay.
All right.
But there is more peps.
More PEPs.
More peps, yes. I created pep, I don't remember the number. 761. What is
Seven something,
What is the
who cares?
What is the number? Pep, what? Pep 758. Yes. So I created this pep with bread count. And it's called allow, accept, and accept star expressions without parentheses. Is descriptive enough for you, Łukasz?
Yes.
Huh?
But then you
Is it scripted
asked people what they thought about it and what did they
No,
think
that's a
about it?
different one. That's a different one. No, we don't. Let's not talk about that one. No, that's a different one. No. We don't talk about that one. Okay. We will explain. But okay, so this pep is actually is the good one. It's the one that people like. So this is because like when you create a context manager, like with several exceptions in the same context manager. Sorry, not a context manager. Sorry, an exception handler.
Same statement.
An exception, except handler. with multiple exceptions in it. So, try whatever except ABC. You are forced to use parentheses, which is kind of like a bit weird because like you can create tuples without parentheses, and then you do this with tuple unpacking, right? Like you do x comma y equals 1, 2, and that works. But here you're forced to use it because like some Python 2 kind of like behavior. So now it's not really Python 2 anymore. That thing is dead, long dead. So now there is no reason to not allow parentheses like in any other place. So the PEP just proposes to just allow parentheses. And it was quite popular, except that there was this like big discussion about like, oh, but what happens if you use as? Because you use as, then it kind of looks a bit funky that you do like, try A comma B, no parentheses, and then you say as E. Like that looks like it's B that is going with the as, not the whole kind of exception, right? So it's like,
which is exactly how the with block behaves, right?
Yeah, exactly, and imports as well. So it's kind of like, so there is this like discussion about people think like, well, yes, but maybe like linter should ask for that and not the language, and there is other people say like, well, but this is inconsistent. So we have decided to force parentheses with the as because it's easier to not add new stuff and then add it later than add it and now say, whoops, that's a bad idea. And yes, that's most of it. I don't think there's a lot more discussion right now, so we probably will submit it to the Steering Council soon. And yeah, that was it. No other PEPs were created. Certainly not a different PEP proposing to remove bare excepts that was clearly not a popular idea. I'm still sad that was not a popular idea, but sure, it breaks a lot of things. I mean, to be honest, like I want to just say something. Like the reason we also create this and the reason we like started the discussion, because the other PEP was also with Brett Cannon and it was originally like something that he wanted to propose, is to just like have an official like position for everyone, right? So it's a proposal, and then people say, well, this is like, we all believe that this is bad, and then now we all know that this is a bad thing, and we can cite this on conversations and future PEPs, and like it kind of gives an official trail on things. So it's not like all the time we propose things that we know that are going to be massively accepted, right? Like that's what PEPs are, our proposals. But yeah, that was clearly a very unpopular proposal, and it makes no sense to actually submit it to the Steering Council. So we didn't. We withdraw it.
All right. So now let's talk about other changes that the team made since the last episode. Let's maybe start with performance improvements.
Okay.
So this is the domain of the Faster Python team, and obviously led by Mark Shannon. So Mark made a bunch of changes, among them two that are particularly interesting to me. So one is called spill the stack around escaping calls. That was a pretty large change, 25 files changed, where stack handling was modified around function calls. So we really hope that this is going to make performance better.
Well, I mean, the idea is that it basically ensures that the stack pointer is not in a register, and it just puts them in different. In kind of like a register, and this puts it in the actual stack of ceval.c. So there is like a balance between possible improvements and the fact that the buggers will not see the pointer, but we'll see.
Yeah. Another change that was interesting was the tidying up of PyCore stackRef, splitting into the global interpreter lock paths and the free threading section. So that is one of the like sort of fun refactors where it makes maintenance of both variants easier.
Right.
Like in the end, like this is sort of a proposal that is part of the deferred reference counts. So like you might remember as a listener that the way free threading is supposed to not be prohibitively costly is for after the GIL removal also have other changes that will make the interpreter more scalable. And one of the ones that is the most important was to make reference counting happen less.
Right.
In fact, today we talked about memory allocation, but we're going to move on and talk about reference counting next time, I guess, and then actually do what people wanted to hear, which is garbage collection. So we can talk about reference counting in more detail, but the important kind of rule of thumb is the less you do of a thing, the faster it is, right? Because it's
It's easy math.
right. Yeah, like the best way to improve speed is not do it. So deferred reference counts, it turns out they might be a good idea even in the presence of the GIL.
Right.
And this is the base idea there, that maybe we will want this on the default build as well. And those changes to split the paths for the GIL and the free threading versions is sort of part of that, which is very impressive to me, that some of the changes that we're having, like pymalloc and whatnot, they end up looking attractive even if the global interpreter lock were to stay.
Exactly. Okay, so now let's move on to new features and enhancements. And let me start with a very important PR that I love. This PR was proposed long ago, if I understand correctly, but it's one that I'm really excited that we're going to have in Python 3.14. So you may hear about Savannah Ostrowski. Is a person that is working a lot in the JIT compiler with our good friend Justin. But in this PR, not in the just-in-time compiler, is on Argparse, which is also close to Łukasz heart, I suppose. And the PR is to add an optional feature to suggest correct names when you use incorrectly in the command line the CLI. So if you say, for instance, like dash action, and then you misspell action, then it will say, oh, did you mean action? So this is a very popular thing that a lot of CLIs do these days, and now Argparse will have the possibility to do this, which is really cool. Another minor thing that, but is very good quality of life improvement is that Storchaka added fraction from number and decimal from number. And these two changes add basically new class methods to these classes to create instances from other number types. So, you don't need to call the constructor in weird ways now.
Yeah, very cool. It's essentially like an obvious way to construct a fraction and construct a decimal.
Right. Then this is kind of an enhancement, more like a new feature, but it basically is a change to replace the enter and exit events with a new event called switched. This PR by Richard Hansen, and this basically is for context variables, which are heavily used in async.io, just to keep context of what is running. So you have a web server, what requests are you handling, and this kind of re-implements the whole thing to use this new switch thing, which makes it, changes all the internal API. So this is a C change. A lot of the changes is in C, and we can talk about it in more detail, but basically just you can allow it to C code can subscribe to changes on these context variables, what we call context enter and context exit. So there is a new enum that and then a new API called pycontext_add_watcher. So these watchers can basically subscribe to these changes, and it will know when it happens. So C code can react to these things changing values. Very cool.
All right.
Okay.
And now we have a change that sounds a little different than what it actually does. So Jelle Zistra made it such that pydoc, which is also known as the built-in help in the Python interpreter, it can now display signatures in source format. What that actually means is that before, if you had type annotations, some of them would be already transformed into sort of unfriendly looking names like forward ref of something and so on, and it would just look ugly. So now that will look more readable and obvious to you again. And interestingly, the way we could arrive at this was that after Jelle got involved with implementing PEP 649, which is undoing the annotations future, and made PEP 749, one of the ideas there was to introduce another library just for handling annotations, annotation lib. The reason why it's a new one is that this is a generic annotation library that doesn't have anything to do with typing in particular. It just does mangling of annotations in interesting ways, also doing with deferred evaluation and so on. And that actually allows you to get annotations of a particular format and with a string and so on and so on. So with that format being value, which means resolve whatever you need on the type annotations front, but just show me what the end result for a human is going to be. now we can have a nicer pydoc, which is a very nice side effect. Like it's going to be user visible. People are going to enjoy that.
Awesome. So now, some important bug fixes. Well, one of the big ones was a fix in async.io TaskGroup, which involves this like internal class called pyfuture. Basically, there is a bunch of reference cycles in that particular implementation, and Thomas Greiner resolved them, basically preventing a bunch of memory leaks that were having between the task and the futures. So that's quite cool.
Yeah, that's pretty cool.
Well, maybe a memory allocator could help detecting those.
Yeah, and another interesting fix was when Sam Gross fixed a data race in the free threading build of ZoneInfo. So it turned out like for free threading builds, ZoneInfos could crash. Now this is fixed. So like we're going to be seeing this sort of for, I guess, like the next release or two, where increasingly HKC fixes are going to be introduced to the standard library to fix sort of a thread safety problem or a data racy problem. In this particular case, that's already an edge case that is not frequent.
Right.
Like just, Py03 actually noticed this, that some tests for time zone conversions would fail with, some panic from whatever. And that happens like very infrequently, but it turns out that was fundamentally because of thread safety problems. So that's pretty cool because, as you can see, this is actually accessed from Rust. So all of this really allows us to make Python more robust, and the free threading in there is sort of the forcing function, but I'm pretty happy that we're making those improvements anyway. It just makes our programming language more rock solid.
Well, and daytime and surrounding modules are particularly like difficult to make thread safe. Like it's one of the last ones, right? Like it needs heavy changes.
You have like global state, and certain things are just relying on C APIs, like from the standard library in C, that are themselves hard to make thread safe.
But things that we have changed in testing, and it has like contributed to making our programming language more rock solid, is Peter Victorin, our deputy core developer in residence. So he made quite a big PR to update the test certificates that expire basically very far into the future. So these are the SSL test certificates that we use, and we don't want them to expire because like that's very annoying. And it basically makes tests break, because when they expire in the future, now you cannot write the test suite of older versions and whatnot. So we have changed this to not expire anymore.
Right. And then one thing that we wanted to point out as well is that in the time that Python is being grown into being more complex and complex now, we started growing not only user-facing documentation, but increasingly internal documentation as well. And Irit Catriel in particular is spearheading this to make sure that the internal docs that we have are particularly comprehensive. So if you are interested in contributing to Python or are debugging some particular weird problem and you need to understand how a given part of Python works, you can now go to the repository and right in the root of that, you're going to find this internal docs directory. And there's increasingly a lot of stuff in there. In particular, since last time, the parser documentation that is very dear to Pablo's heart moved there, and the garbage collection documentation moved there. So you can essentially learn a lot about how Python is built internally from there, and it's all in very readable markdown. So
right,
I invite you to just take a look. You might be surprised how you're gonna learn,
because you mentioned the two documents that I wrote. So,
yeah, exactly.
So actually, I want to also thank publicly Edith, because one of the reasons he wanted to move this from the dev guy is that now if we keep this on the CPYTHON repo, those documents are going to be kept in version control. So you will know how the thing was designed at the time we had the document there. So if we change the thing, now there is not only one version of the document that refers to the latest version. You can see how the thing was designed in the past, and we keep changes to that so close to the source code. And she made a very good job because the original thing was in Sphinx, and she moved this to Markdown. And originally, for instance, I raised a bunch of concerns because like the images don't work really in Markdown and whatnot. But obviously, this is GitHub Markdown that actually renders images like in the README. And like
this works really nicely. Like I like this.
Yeah.
So the dev guide is also versioned, right? But
no, but like
those repositories are independent.
yeah, so it's very difficult to know what version of the document corresponds to Python 3.7 or 3.8 or 3.12, right?
True.
So I spent a lot of time writing these documents, and she made a very good job at preserving even the admonitions. So really, really, really good job.
Yes. So the tricky bit, essentially, with a dev guide that is external is not just that like it's tricky to map one version to like one commit to another, but that honestly we are now maintaining multiple versions of Python, right? So it is very helpful to be able to see in a different branch that like, oh, okay, like those things used to work differently in Python 3.9. We still maintain that ancient version of Python. So, it's going to be way different from looking at Python 3.14. There is a fantastic book about Python 3.9 internals, right? That Anthony Shaw wrote about, how CPython is built. Part of that is still current. You can still learn a lot of that, and you can still check out Python 3.9 and actually learn everything about it. But you're looking at the main branch right now, well,
Right.
let's just say things changed.
Quite a lot.
Quite a lot.
Well, one last thing before abandoning this section that I have here in my notes, but we didn't mention, is that the change also to make the certificates expire was also made in collaboration with Alexander Kanabin, which is a contributor from Berlin, Germany, that made the change together with Peter.
Oh, that's cool.
Yeah, very cool. And the last change, which is an Easter egg.
No, we cannot talk about this.
No, okay.
No, censorship. Like you don't spoil Easter eggs. Come on.
No changes. Okay, sorry.
There are no Easter eggs. Those rumors are false. We strongly deny them.
Okay. So you will never know the Easter egg.
All right. So with that, I hoped this deep dive on memory management wasn't too boring. It's not for us because this is where the weirdest bugs hide when you're actually using the memory management. Like most of the time, you're not making changes to it. You're just a user,
Right.
and still we fail.
Yeah.
We fail so often.
Yeah, almost every single time you're welcomed by this. Like quite surprising. Like literally yesterday, I received one of these bugs. Quite annoying as well. Like I was testing this new. It's one of the bugs I found in these hooks that we had in 3.13. Turns out that we are not calling the hook on destruction in all places. So you just keep the objects that are alive in one place, and then you subtract from the set every single time you see a destruction. Because we don't call destruct on all the objects, then you think that some of the objects are still alive. So you try to print them. Like funny things will happen. In particular, it will succeed printing them even if they are dead because nothing has been using the memory blocks, but it corrupts memory. So when you allocate something else, totally different things, pymalloc will say, what is this block? It's like corrupt, and it will just segfault. And that happens like very far away from when you print the invalid things.
All right. So hopefully now you're going to be more equipped to prevent those sorts of errors yourself in your code. We always just invite you to try build your own Python and just play with that. Correct me if I'm wrong. Like, are we actually able now to run non-pydebug C extensions from a pydebug build? I remember
It's API compatible.
Yeah. So now,
but from last release 3.12 was also API compatible.
Yes, exactly. Like I remember
Who
that's
made that
recent.
change?
I want to say Victor.
Victor did the change. Yes.
Yeah.
He also made the change of making. Actually, this may be as far as 3.8.
I don't think it's as far as 3.8.
Yeah, I think it's
recent.
3.8. I think it's 3.8 because he made this change that is very funky, but precisely to this end. So a C extension is using the libpython, like it's using the API from Python. So it should link against libpython. It would say, I need the symbols. But he made this change, so the symbols always come from the main binary. This linking of C extensions is quite annoying to deal because when you build the C extension, as it's not linking anymore with libpython, the linker freaks out. It's like, I have all these fucking undefined symbols. Who is going to satisfy them? And then you need to say, chill out, man. They will appear from fucking Python. And you guys, what? They don't unless you compile with the secret sauce. You know what's the secret sauce? The secret sauce is export dynamic. It's a linker flag that says all your dependencies. Like so for instance, you're the Python binary, you will have dependencies. For instance, libpython.
Yes.
But you will have, I don't know, like libc and shit. So grab all of those dependencies and grab their dynamic tables, and then you put that in your dynamic table. So now you say, I made this. Literally. So you know what happens? Like if an extension says, buddy, I need malloc, then libc doesn't say, I have malloc. No, it's fucking Python that says, I made this.
It comes from Python. Yeah.
It's very annoying because like how many pointer references do you need now? You need 2 pointer references.
Yeah.
Why is that? How is that possible? Because you will like obviously Python doesn't have malloc. So what Python does is that it will put malloc on the PLT, the procedure linkage table, and that will jump to libc's procedure linkage table, and that will actually like do the malloc. Yeah, you see, in the what's new of Python 3.8, there is a big section called debug. Build uses the same API as release build. Python now uses the same API, whether it's building release mode or debug mode. Python 3.8, man. Who released this? Who released this? Who?
I just thought it was so recent, man. And now this version is end of life.
Man, this version, literally this paragraph is below positional only parameters that I added. So this looks ancient now. You fail. Oh no.
And on that terrible disappointment, see you in 2 weeks.
See you in 2 weeks.